Okay, Scott, you are good to go.
Okay, thank you. Good afternoon. My name is Scott Hampton. I work for the Antelope Valley Union High School District. I'm the vice chair of the Antelope Valley East Kern STEM Network. We work to ensure that students within this region can demonstrate the knowledge and skills that are necessary for success in education, in work, and in their daily lives. So one of the goals of the network really is to develop partnerships. And we're developing partnerships in education, business, and community so we can increase efficiency, innovation, scale, and sustainability of quality STEM teaching and learning within the Antelope Valley and East Kern STEM network. To show our partnerships today, we have some guest speakers. The first one is Shane Furlong. He's with a spaceship company who will be talking about the use of carbon composites in the space vehicles. Then we're going to have a short student presentation from the Mojave Junior Senior High School Engineering Robotics Club. And third, we'll have Dr. Joseph Kalman from Cal State University Long Beach, who's going to be speaking on how it's made solid rocket propellants. So thank you.
And I apologize. We are having just a little bit of technical difficulty on this end. So Shane, I'm going to go ahead and ask you to go live, and you can just introduce yourself. And as soon as we've got your video up, oh, sorry about that. Looks like our video is back up. So we're going to run into that now. Again, we apologize for the technical mishap.
Shane Furlong, and I'm going to talk to you all about the use of carbon composites in space vehicles today. Just want to give you a quick background on myself. Grew up as a complete airplane nerd with a complete fascination with anything that flies. I still try to run outside whenever something flies over my house. I knew I wanted to be involved with the design and build of aircraft. I wanted to be part of whatever the next greatest innovation in aerospace was. And I thought that composite materials would play a major role in the future of aerospace. So I went to Auburn University to study the polymer and fiber engineering, which is a unique mix of chemical and mechanical engineering. During my summers, I interned at Gulfstream Aerospace, where I worked in their advanced composites lab, helping to evaluate different composite materials and structures. During my master's research, I focused on a very unique braided composite structure that provided the benefits that traditional composites could not. A good lesson that composites come in a variety of forms that are still being invented and developed today. I joined the spaceship company because I wanted to be part of a team that was working to accomplish something that has never been done before, giving ordinary people access to space. And composites play a crucial role in making that dream a reality. So, before we talk composites, let's talk about Virgin Galactic's vehicles, which were designed, built, and tested by this spaceship company. We have two vehicles, but the one we'll focus on today is our spaceship, Spaceship 2, also known as VSS Unity. This all-composite spacecraft is designed to carry 6 passengers and 2 pilots on a suborbital trajectory into space, before gliding back to Earth and landing like a glider, as seen in this photo. The other vehicle that is equally important is our mothership, or carrier ship, known as White Knight 2 or VMS Eve. This is a very unique twin fuselage, all composite aircraft designed specifically to carry Spaceship aloft under her center wing. Spaceship is mated to White Knight in the hangar where passengers climb aboard Spaceship before White Knight takes off like any normal aircraft and climbs to release altitude. White Knight 2 climbs to its release altitude of about 50,000 feet. Once all the systems are checked out and we're go for launch, White Knight releases Spaceship into a free fall. White Knight then returns to the airport and lands just like any other normal aircraft that's just dropped the Spaceship. Moments after release, Spaceship 2 ignites the hybrid rocket motor and trims her nose upwards. The passengers experience the ride of a lifetime as Spaceship accelerates past Mach 3 and climbs towards space. So now you know a little bit about our aircraft and spacecraft. Let's talk about how they're built. So, without composite materials, it would be very difficult to build a spacecraft that is both lightweight and strong enough to carry passengers to space. In this image, you can see Spaceship Unity on the left. This spaceship is currently in flight test in New Mexico. On the right is our next spaceship, currently in final assembly in Mojave, California. You can see that below the shiny white and chrome livery lays the utilitarian black carbon fiber that makes this vehicle strong and lightweight. As you can see, nearly every structure on the vehicle is fabricated from carbon composites. So let's talk a little about composites, what composites are, and how we take them from rolls of flat fabric material and process them into airworthy structure. A composite material is one that combines two very different materials, excuse me, one that combines two very different materials into one, which results in a new material with attributes superior to the original constituents. The whole is greater than the sum of the parts. In the broadest sense, composites are made up of two parts, a reinforcement and a matrix. Reinforcements typically come in the form of a fiber, and matrices come in a wide variety of types, ranging from polymers to metals or even ceramics. Composites, in the most general sense, have been around for a long time. Think of rebar in concrete structure or straw in a mud brick. But what we're here to talk about today is high-performance composites, which are often carbon fiber reinforcements in a polymer matrix. Composite manufacturing processes vary widely, each with their own set of advantages and disadvantages. Shown here are three methods of building composites, spanning from one of the cheapest and straightforward to the most expensive and intricate. Keep in mind that we're not even beginning to scratch the surface on the different ways to build composites. Wet layup is composites at its core. You take liquid resin, you mix it in the appropriate ratio, and spread it onto your fabric reinforcement. This yields a composite structure that is relatively cheap to build, but it requires a lot of manual labor. It's prone to errors, and it's a bit heavier than you'd like. It also has a lot of variance, which we'll talk about later. Pre-preg layup is one of the most common methods of building high-performance aerospace composites today. This method of manufacturing is differentiated from wet layup in that the resin or matrix is already added to the fabric reinforcement. So all you have to do is cut it to size and laminate it together in different layers. This is a moderately expensive method, but yields a relatively strong and lightweight part that is much more repeatable than a wet layup part. Finally, automated tape placement, or ATP, is an automated method of manufacturing composites using CNC-controlled robots to deposit the composite material exactly where you want it. This automated equipment, of course, costs a lot up front, but the quality of the parts and benefits from automation make it a valuable option to consider. All three of the methods have advantages and disadvantages. It is an engineer's job to evaluate all methods of manufacturing a composite, evaluating properties, production rate, cost, and a myriad of other things in order to determine which is the best method for a given structure. So why should we use composites? The most appealing attribute of composites is the high performance they offer, while remaining remarkably lightweight. Where composites really shine is their strength to weight ratio, or specific strength. There are plenty of materials that offer high strength and stiffness, but at what weight penalty? If we're going to space, every ounce counts. The plot on the right compares specific strength and specific stiffness. In this plot, the ideal material that is the strongest and stiffest, but is also the most lightweight, is in the top right corner. As you can see from the yellow region, ceramics get pretty close, but they have their own host of processing and manufacturing issues. The next closest region is the dark purple region, which represents composites. Composites also give us the flexibility to create complex curvatures. Think of the complex flowing curves on most high-performance aircraft and spacecraft. These would be more difficult to produce with traditional metallic processes. Another advantage of composites is that they give us the ability to only add material and strength where we need it, which allows us to create optimized structure. Composite fabrication is an additive manufacturing process, similar to 3D printing, where we don't need to remove material we don't need. It's simply not included in the design from the start. Composites have a long list of other advantages, such as fatigue and corrosion resistance, the ability to reduce part count, and low observable properties, good for stealth. So if composites are so great, why don't we build everything out of them? Well, there are of course disadvantages and difficulties that composites bring along with them. One of the most prominent ones is the high cost of both the material itself, in addition to the complicated and nuanced manufacturing process. The manufacturing process is relatively difficult, providing many different opportunities for errors to result in non-conformances or scrapped parts. As such, composite technicians must be highly trained and skilled in their trade. Composites can also be quite tricky to inspect for damage and defects. Likewise, repair to such damage is often not very straightforward. In this image of our next spaceship in assembly, you can start to see the intricacies and details of the numerous composite parts. Every one of those had to be meticulously inspected. Finally, a point that is often overlooked by those not familiar with the unique aspects of composites is that these can be highly variable and process-dependent materials. So what does that mean? Well, anyone could Google the properties of aluminum 6061 and gain a solid understanding of the properties and capabilities of that metal. Composites are quite different. They of course depend on what reinforcement and matrix was chosen, but there's so much more that can change their properties. From the temperature of the facility that it was laid up in, to the length of time it took to lay up, to the skill level of the technician, or even the altitude. All of these can affect the final properties. Additionally, this means that the material can be highly variable, something we need to use processes and statistics to account for. All of this makes developing industry standard properties to use in design and analysis very difficult. You won't be finding the answer to this question on Google. So how do we control the variance and ensure we understand the capabilities of these process-dependent materials? How do we go from a roll of carbon fabric to a finished airworthy structure, such as this composite assembly, which forms part of the aft wing section of a spaceship? We must carefully and strictly control the processes. A process specification is a step-by-step description and guide that controls every aspect that could influence the outcome of the process. Every aspect from storage to layup, curing, trimming, inspection, assembly, and install must all have a specification that states what is acceptable and what is not. These process specifications, alongside the engineering definition, ensure that the same part can be built many times and have the same properties and attributes each time. These processes ensure that the material properties are both optimized and consistent for every part built, no matter the technician or the day of the week. So once we know we can manufacture the same composite material reliably through processes, we need to understand its properties and behaviors. Composite material undergo a myriad of different types of tests to determine mechanical and physical properties. We need to quantify mechanical properties such as tension, compression, and shear strength and stiffness. Physical properties such as density, surface temperature, and coefficient of thermal expansion are also critical. In the images, you can see two very common destructive mechanical tests used to determine tension and compression strength and stiffness. On the left is a tension test, where a carbon composite is pulled in tension until the fibers fail in tension, rather explosively. On the right is an image of a composite laminate being loaded in compression. Here you can see how eventually the matrix can no longer sustain the load and it fails in a very different manner than the tension test. Oftentimes, this testing is performed in different environments to understand how the material behavior changes at extreme environments. We perform cold testing in order to understand how the composites will react to the cold temperatures experienced at high altitudes and in space. We also evaluate high temperatures to understand how the material weakens during periods of high temperature during re-entry or exposure to the rocket motor plume. So now that we have test data for the various material properties, what do we do with them? Because of the inherent material variance of the composites that we talked about earlier, we need a way to ensure that the material properties used to design and analyze structure are safe or conservative. The test data is reduced via statistical methods such as A basis or B basis in order to generate what we refer to as allowables. These allowables are then communicated to the design and stress engineering teams for design and analysis of composite structure. However, it is crucial that processes continue to be followed such that all material properties continue to match the test data and published allowables. This ensures that the properties measured from the test coupons on the prior slide are still applicable to the aft wing and boom structure that is seen being assembled in this image. In summary, without these lightweight and high-performance composite materials, designing and building a spaceship that allows ordinary people to become astronauts would not be possible. I hope you enjoy this quick look into what it takes to build carbon composite structure capable of taking humans to space. Thank you for your time.
Well, Shane, thanks for that fascinating look at carbon composites. We have a few questions. Would you tell us about your career path and how you ended up with your current job?
Sure thing, I'd love to. So like I mentioned in the video, I always grew up loving aircraft and spacecraft. So when I decided that, composites might be a good into the field, I decided to go to school and focus on composites, but always keeping in mind that, I wanted to end up in aerospace working on aircraft and spacecraft. So, I studied hard and always looked for opportunities to get more involved with things that I thought might help me get closer to aircraft. And so, whether that was learning some things on the side that might be, more applicable to metal shop or, different statistical methods, I always had my eye on the sky, I guess you might say, and really wanted to make sure I was learning all I could so I could be as diverse of an engineer as I could be.
Well, great. What kind of training or education do you think kids need to do something like you do?
There's, obviously everything that you're learning in school is very applicable, but, what I find day to day, I think having the hands-on knowledge and from a very early stage in your career, you should be, understanding the actual, realities of what it means to build something, put your hands on it, get dirty, and really understand what it is that you're trying to design and build.
That's great. Do you think commercial or getting people to space will become a reality in our lifetime?
I think it might be a little bit biased, but of course, Virgin Galactic and a few other companies, are getting closer to that every day. The technology is out there, and I think there's certainly a desire for everyone to go up and see the Earth as the astronauts see it.
So a follow-on to that would be, do you think lunar or space habitation for the general public will become a reality?
Yeah, definitely. The human race has always been driven to explore, and space is certainly the next frontier to conquer. So in order to do that, we're certainly going to need a place to call home. So I think the moon is probably a great place for that.
Great. So who inspired you?
That's a great question. There's certainly a lot of people out there that have been inspirational. When I think in terms of, specific to aerospace, I think one of the people that I always thought was, a really important figure was Kelly Johnson, the founder of Skunk Works. He had a really significant impact on aviation. And some of the aircraft that he designed are still some of my favorite. I would definitely recommend reading the book Skunk Works.
Wow, great. Looking back, is there any decisions you made that really helped you get to this point in your career?
I think staying focused and really, if you can pick something out that really speaks to you, you're really interested in, it's not just a subject you study in school, but something that, you daydream about, something you think about all day. I think you can use that to really focus your energy on, and you can certainly succeed.
So obviously you're in the space sector. Do you think that's the future of business in the Antelope Valley for the next 20 years? Or do you think there might be some other opportunities around here?
It certainly seems like that'll be a big part of it. There's so much history out here, but I think one of the things that drew me to this area is that you never know what's around the corner. None of us can predict what the next greatest step might be. It's always interesting to me to look up in the skies over the Antelope Valley and not necessarily know what that airplane was that flew over, because there's always something new that's taking to the skies. And so, I think space is definitely a big player, but you never know what's next.
So what dream did you have as your child?
I think one of them was certainly, just being part of something that either hasn't been done before or something that very few people have gotten to experience or do. And so, being part of a team that, helps build a new aircraft that doesn't look like anything else out there that's flying, that, someone sees sitting on the ramp or flying overhead and goes, what in the world was that? That I think that's really cool.
That's awesome. What was your biggest challenge to get where you are, and how'd you overcome that?
That's a good one. I think one of the most challenging things is time management, especially, growing up and going through high school and college. That's one of those skills that you just kind of have to you learn as you go, and being able to identify the tasks that deserve and demand the most of your time and focus in order to make sure that you succeed in them.
So what do you think will keep the space business competitive, and how do you think that will draw talent into that company or that industry?
Mm-hmm. I think one of the coolest parts about space is that, it's such a leading edge thing. There's so very little people or items that, get to, push that boundary. And so, that boundary is always going to be expanding. So we've always got to keep inventing things, right? We always need to continue to learn and grow. And so it kind of seems like a wave, right? It's just going to keep on moving. And, space tends to be at the forefront of the aerospace part of it. So I think there's always more stuff to learn, more stuff to invent.
So when you were young, did you expect have the job you have now?
Not at all. I've got to admit, I was probably a little bit more of an airplane geek than a space geek when I was a little kid. So I definitely wouldn't have, but it's nice to be part of a company that has both aircraft and spacecraft.
So kind of in closing, what would be a couple really important things that you want kids to remember about their education?
It's hard to pinpoint one or two specific things. The thing that I think about every day is that, we're learning every day. It's not a destination, right? We don't wake up one day and we know it all. It's important to keep learning, go find the things that you're interested in and go learn more about those things. It's going to open more doors.
Well, thanks for talking to us today. We really appreciate sharing, and thanks for joining us.
Yeah, of course. Thanks for having me.
Hello, I am the engineering instructor at Mojave Junior Senior High School. I've got a short presentation here for you about the Mojave Junior Senior High engineering program pathway. Hopefully I will tell you a little bit about how we feed into our school with Summer Science Academy, a little bit about the Mojave Middle School, and the Mojave High School engineering program. So our feeder school, the elementary school, we take some of those kids in the summertime in the Science Academy and teach them, things like what drives the weather and how energy is conserved in different environments and how to use measurement devices. It's very fun for them. They get very excited about engineering and science topics. Here are some of the kids using multimeters. They're also on the right-hand side experimenting with rubber balls, and we chill those rubber balls, we heat those rubber balls, and then they measure how high they bounce depending upon how or what height they've been dropped from. So it gives them some idea of the energy that's contained in the heat that the balls have when they're dropped. Moving on into middle school, our kids get a lot of hands-on experience with tools they may not have been introduced to before, industrial style tools. They do some design, drawing, a lot of fun activities, measurement activities. They learn about solar energy. Here the kids are designing, making, and operating their own hydraulic arms or battle bots, where they compete to see which design is better. And they learn an awful lot about construction and hydraulics and pneumatics and have a lot of fun in the process. So this student is he's got a cam operated device. This is a high school student who designed this on a CAD program and then printed out the essential components. There was a lot of problem solving going on there, but this was a little out of the usual. So I thought I would share a little bit of what he did, and we're proud of him and where he's gone. The group on the left-hand side are high school students. The group on the right are some middle school students, but the ones on the left are demonstrating their model of an elevator, where they programmed a controller and built the model device where you press a button, the elevator responds to that floor, and then will return to the first floor on a secondary button push, or after some time has passed, it returns to the first floor, its default place. So that models what would actually happen with an elevator. On the right-hand side, those students are experimenting with photovoltaic panels, and they are pointing the photovoltaic panel directly at the sun or away from the sun, and they're measuring how much energy is produced by that photovoltaic panel, and getting some idea of where we get some of our energy from the sun. These high school students are demonstrating their generator. So they spin their axle, the coil of wire moves past a magnet, and it generates a electrical current, and they try to make a light bulb flash, and they measure the amount of electricity that's produced, and then they try to reverse it so that it will spin when you add an electrical current to it. Finally, we have a robotics team. These are mostly middle school students, or they were middle school students at the time. And they compete with the VEX robotics team that is a worldwide competition. Ours are primarily located here in Kern County, and they do well, and we're really proud of them. We want to give a big shout out to Northrop Grumman, who has financially supported us in a big way, and we appreciate that. It helps keep our program going. Thank you very much for your attention, and we're proud to be from Mojave Junior Senior High School.
Well, thank you. Next is Dr. Joseph Kalman from CSU Long Beach.
All right. Well, thank you. Thank you, everyone, for attending. My name is Joe Kalman. I'm an assistant professor at Cal State Long Beach in the Mechanical and Aerospace Engineering Department. I'm going to talk a little about solid propellants today, basically going through the process, how they're made, and some of the research that we're doing to try to understand the underlying science behind that and ways that we can improve that later on, which is of course, our final goal. So first, a little bit of background. I run the solid propulsion and combustion lab. And so in my lab, we focus on trying to understand a variety of different aspects of solid propellants, other solid fuels and oxidizers that are used in rockets and other propulsion systems, and trying to make measurements on those and again, try to develop new technologies. But one of the questions that we really try to answer, among some other ones, is how can we incorporate additive manufacturing or 3D printing, as it's more commonly known, into propellant manufacturing, and specifically, how does additive manufacturing propellants, how does that affect the final propellant that we make? And so that's sort of one of our main objectives in my lab, is to try to understand that aspect of it. But first, I want to talk a little bit about some background. So when I talk about solid propellants, these are solid rocket motors that are used in a variety of different applications. They're military applications. You can see an image at the bottom here of a missile, but also in space exploration. So in for instance, the space shuttle solid rocket boosters, those are of course solid rocket propellant. We have these different applications where we're trying to understand how material, like you see towards the right here, how it burns, how it's made, and how it overall behaves. And so this solid propellant is composed of both an oxidizer and a fuel. And these are both solid materials that are combined in one, which you can see this maroon-like cube here. And you can think about the solid as being the fuel, similar to the gasoline in your car engine. And the oxidizer is basically where the oxygen comes from, right? Again, for your car engine, that would be the air that's coming into your car engine. And so in the solid propellant, we have both these fuel and oxidizers already mixed together in this single structure right here. And the goal with this is to use this material to produce thrust, right? To get our rocket going forward. So in terms of a few short steps, right? The idea is that we burn this propellant. Remember, it's a fuel and oxidizer. So just like in our car engine, it's a combustion reaction. And so in doing that, we produce a lot of heat, a lot of energy output, but we also produce a lot of gas. So this solid material, it doesn't stay solid. Once it burns, it's in the gas phase. So now you produce a lot of gas, and now this can be expanded out through a nozzle, and that nozzle will help us produce thrust. And here you can see an image of the space shuttle with this plume as that the combustion products from the propellant are being expanded out of the nozzle, and that's propelling the rocket forward. All right, so really what I want to talk about today is where does this propellant come from? And of course we make it, right? We're engineers, we're scientists, we make things. And so we're talking a little bit about that process, but I do want to emphasize first, I have it highlighted here for that reason. We're going to talk about how to make a rocket propellant, solid rocket propellant. And I really want to make sure everyone knows not to try this at home because it can be dangerous. The different ingredients that we use in propellants and the final propellant itself can be very hazardous. So You definitely don't want to play around with this material if you're not familiar with it. That's why you want to make sure you have the proper knowledge and facilities to handle such material. With that being said, let's talk about it a bit more. And I want to talk about it in relation to baking a cake. Of course, most of us are very familiar with cake, maybe not so much propellant, but in fact, they're actually made in a very similar process. And so you think about the different the processes, the steps in baking a cake. First, we measure our ingredients, then we mix them together, we pour it into a cake pan, and then we bake it, right? So we're going to look at each of these steps one at a time, and for a cake, and then also relate that to how we do something similar with solid propellants, and we'll talk about the details of that. All right, so first let's think about our ingredients. We know we have a whole bunch of different ingredients that we haven't listed in a recipe to bake a cake, but what I want you to do is not think of all the ingredients as individual components, but think of them as different categories. Right? We have the first category is liquids, right? So we have things like egg, there could be some milk, maybe vanilla extract, things like that. These are all different types of liquids that we put into our cake recipe. But we also have powders, right? Of course, we have things like flour over here, sugar. In this case, we have cocoa powder if we're going to make a chocolate cake. And of course, these are all going to be mixed together eventually. But I want you to think about these different ingredients as different classes of ingredients, because with propellants, we have those same types of classes of ingredients. Obviously, the materials themselves are different. So the first is the liquids. Here we have a polymer, and in this video on the right, this kind of shows you the consistency of this polymer. This is a molecule that's a long chain of carbon atoms and hydrogen atoms, and they're all sort of interwound together, which gives us this very thick, viscous looking nature, like syrup. Well, this polymer is actually used as the fuel in our rocket propellant. It's also used to basically hold everything together, right? Just like in a cake, the liquids basically hold the powder together. And likewise, we also have powders in our propellant. One example of that is ammonium perchlorate. Ammonium perchlorate is an oxidizer. It's a solid white powder. It basically contains our oxygen. So when it heats up, it releases that oxygen in several reactions, and that's what gives us the fuel and oxidizer combination between that and the polymer. We can also add other powders into our mixture, such as different metal powders, like aluminum, and that actually acts as a fuel in this case. So these materials here are actually exactly what the space shuttle solid rocket boosters were made out of, in general at least. And that's not to say that these are the only ingredients that we can use, but these are some of the more common ones that we have here. And so in this image on the left, you see some other powders here. The work that we're doing right now in the lab to understand this process, we're using glass beads. And the reason why we're using glass beads is that they're not reactive, right? We don't have to worry about the propellant igniting when we don't want it to, because we're not introducing any oxidizer. So that's done for safety. And so some of the images and videos that I'll show from now on, we'll look at these mixtures with the glass beads. Okay, so that's the different ingredients. Of course, the next step when we're baking a cake is to mix them, right? And so we have a KitchenAid type blender or mixer that perhaps many of you are familiar with. And of course, the goal here is to take our liquids, our powders, all the ingredients, and mix them together so it's uniform. We don't want clumps of flour in one spot, eggs in another spot, right? We want everything to be uniform throughout. And even though from our naked eye, it seems like this is a uniform mixture, on the microscopic level, is actually, you can actually tell the difference between different materials, and we'll see that later on. So when we make a propellant, we actually use similar types of mixing processes. So traditionally, we use these same types of mixers that you see in the kitchen, except they're usually a little bit bigger because we're basically making more propellant than we would in terms of making a cake, or in terms of batter for a cake. But they're also explosion proof. Remember, these propellants have fuel and oxidizer together already. So that presents a possible explosion hazard. So that's why these industrial sized mixers are usually a little bit more robust than the one you see in the kitchen, but it's the similar type of process. Now, another process mixing type process that we're looking at right now is called resonant acoustic mixing. And I'll play this video here, which is slowed down so you can see things a little bit easier. And resonant acoustic mixing is a newer technology that we're investigating, and others are as well investigating, to mix propellants more efficiently. And so what you see here is this base of down here is oscillating at 60 times per second, and it's accelerating as fast as 100 Gs. Right, so you're providing a lot of acceleration, a lot of force into the mixture in this container here, which contains our mixture of ingredients that we talked about on the previous slides. And so the goal here is to really mix this. And what we're doing in my lab, at least in part, is trying to understand this mixing process a little bit more. And I'll talk about that in the second part of this talk. Okay, so once we have our batter mixed, right? So going back to the cake analogy, we put it into our cake pan, we put it into the oven, right? And when we put it into the oven, what we're really doing is creating a high enough temperature where the chemistry can start to occur. So when you're baking something, it's really a chemistry experiment. And what that allows you to do is take your raw ingredients, your batter, and create a final product, which is your cake, right? Something that we want to eat and use afterwards. Likewise, propellants go through a similar process. Now we pour this mixture of ingredients into what we call casting hardware. This casting hardware is basically there to give us the shape of the propellant that we need for our rocket motor. Right? And so there's different types of shapes that we can make depending on what we're trying to do, what the engineers and scientists designed this rocket to do. But the idea is that we pour it into this mold, and again, we put it into an oven. Put it into a little bit lower temperatures than your kitchen oven, but the same idea is that we allow chemistry to occur. And so remember the polymer that I talked about a few slides ago. I said these were long chains of a long chain molecule. Well, when we put it in the oven, the chemistry that's occurring is allowing those two molecules to link up to each other. Basically, we're linking them together. And by doing that, we take this polymer and make it into a rubber. And this rubber is sort of what you see in this image here. This is our mock propellant with their glass beads and the polymer. And so the glass beads are being held in place by the polymer. And in the same hand, in a real propellant, that polymer is now also acting as our fuel. Right, so you can see we went from those mixture of ingredients to, again, a solid piece of material that contains all of our ingredients, just like when we have a cake. So I want to sort of turn the tables a little bit and bring up, why understand the science, right? So we know how to make a cake. We know how to make propellant. So why are we interested in understanding the science here? Well, think about it this way. Anybody can bake a cake, but not everybody can bake a good cake, right? You want a cake that comes out that's moist and doesn't fall apart. But if you do things wrong, it can come out and crumble, be dry, and not really taste very good, right? That's not what we want in a cake. Similarly, in a propellant, we don't want it to fall apart. We want it to do what we designed the rocket motor to do, and that's to produce thrust. So by understanding the science, it allows us to understand the process behind it, this manufacturing process, and find ways to improve it. So, for instance, the resonant acoustic mixing, right? This is something that we can potentially understand how we can improve the mixing process so that at the end of the day, we get better, stronger propellants that get the job done more efficiently. The other aspect, the reason why I want to understand the science, is that there's always new technologies developing. And so we all know about, or at least have heard about 3D printing or additive manufacturing to some degree. And so if we really want to be proficient at 3D printing propellants, we need to understand that underlying science, the physics and chemistry that go into this process. All right, and that will really help us make the next generation, the next improvement with propellants. So what we're looking at in my lab, one of the projects that we're studying, is really thinking about what happens when we mix a solid and a liquid, right? Think about what happens when we have our powders and our liquids that we mix together. What's physically occurring? This is something that we call the wetting process. And I'm going to talk a little bit about that and some of the work that we're doing with that right now. So first I want to draw your attention to this top image here, especially the left side of that image. Think about when rain hits a window or just water falls onto a piece of glass. You typically see it bead up like this, right? You have these droplets, they form on here. And a lot of times we don't really think much about it. But if we understand the science behind what's happening when this water interacts with the glass, we can then understand how to improve this. So for instance, if we change the surface of the glass, we can get something that we see on the right-hand side here, where it basically spreads out everywhere. And in a propellant, when we're mixing the solid particles and the liquid together, we want something that happens similar to what's on the right here. And I'll talk about that in a moment. So what we're doing in my lab, one of the experiments, is we're trying to understand the interaction between different propellant ingredients, just like the interaction between the glass and the water in this image here. And so if you learn about the surface tension of these materials, the surface tension is going to pull this liquid droplet. This blue figure here is the liquid. The black portion is the solid. And we're going to form this droplet on top of the solid. And depending on the surface tension of these different materials, we'll create a certain contact angle, is what we call this angle right here. And this contact angle tells us how well the liquid wets the solid. Basically, how well will it spread out over that solid, and eventually how well will it adhere to that surface when we talk about propellants. And so the goal here is to create very small angles between the liquid and the solid, right? Sort of like this right side here where it spreads out evenly. And this is what we call hydrophilic. Conversely, if this angle is large, we get something called that's hydrophobic. And that's what you see here. That's why the water beads up on it, because of that mismatch. So what we're doing in the lab is we have an experiment, and here's an image of that experiment. We have a camera with a lens set up. And then at location B right here, we have a stage where we put our sample. And with our sample, we put a small droplet of the liquid polymer on the powder. And then we have a light back here to give us some nice images. Right. So the goal of this project is to understand how these ingredients interact, because at the end of the day, we want to make sure that our ingredients interact well, and we get that low contact angle, so we get better adhesion between our solid particles and the liquid that's surrounding it. So here are some images of those experiments. You can see a variety of different angles and droplet shapes here between ammonium perchlorate and some of the polymers that we're studying. And right now we're still looking into the details of understanding why do these different polymers change this contact angle. So when we look at building a propellant, making a propellant, we can choose our polymer that we want to use. And we're going to choose that polymer based upon its properties. So we're trying to understand what aspect of the polymers give us the best degree of wettability, right? What allows this angle that you see here to be as shallow as possible, right? And again, that's going to really give us the best adhesion that we can ask for in the propellant. Right? And so to kind of demonstrate that, I have a couple of images of some micrographs from a couple of different works here of different propellants. So this image on the left, all these objects you see here, these round objects, these are different particles. This is ammonium perchlorate or aluminum particles, the light gray. And these are all held together by the binder, this dark gray in between these particles. That's that polymer that forms into a rubber. Now, it may be tough to see with everything, with all the particles in here, but the binder, the polymer, adheres relatively well to the particles, right? So that's a good thing. That means it's going to make our propellant strong, have good mechanical properties. But you compare that to something on the right-hand side, notice these dark rings around the particles. This is what we call de-wetting. This is a result of that contact angle being relatively large, right? So basically, we're not getting a lot of adhesion. And so when we finish making our propellant, the binder doesn't want to stick to the particle. And that means our propellant is going to be weaker mechanically, and also it gives us additional area for the flame to spread. And if the flame spreads, that means we overpressurize our rocket, and that can destroy our rocket. So you can see how important it is to be able to understand the interaction between these different materials in general, but also during mixing, right? And so that's going to help us develop new propellants and apply some new technologies. So some future developments, of course, we talked about the different, the way that we make propellants now and some of the new approaches. But what we really need to do, and what we're trying to do in my research group, is to understand how these materials interact, how they're wetted, how they mix together. And we can work on developing surface treatments, like you saw with the water droplets on the glass, to modify that wettability so we get better adhesion between our ingredients. So when they mix more uniformly, and when they cure after putting them in the oven for a bit, we get strong propellants. And of course, by understanding this underlying science, it allows us to start incorporating additive manufacturing of these propellants. And the idea of additive manufacturing is that now we can really customize a rocket motor for whatever mission we want, whatever we see as appropriate. And so with that, I'd just like to thank everyone for their attention. Also, I'd like to acknowledge Louise Cruz, who's one of my students in my research group at Long Beach, who took those videos, and also the California Aerospace Technology Institute of Excellence and the Air Force Research Lab for funding this work. This helped support us in getting some of this work done. And so with that, I'd be happy to take any questions, and thank you again.
Well, great. Thanks, Dr. Kalman. One of the first questions is your university the only one that does this with rockets, or is there other ones that do this?
That's a good question. So there are other universities that study solid rocket propellant, and there's a lot, throughout the United States, especially in the Midwest, some big universities, and of course we're all studying different aspects of the propellants, but there are others that do this as well.
So, how dangerous is it to make rocket fuel?
If you don't know what you're doing, and you don't have the proper facilities, and you don't know what precautions to take, it can be dangerous. Remember, these are materials, when mixed together, that can be, or typically are, classified as explosive. And so it doesn't mean it's going to blow up in your face, but it has that potential to. So that's why it's something that is pretty hazardous. And you need to make sure you have the proper facilities and proper training before you handle these types of materials.
Oh, good question just came in. Can solid rockets be turned on and off?
That's a good question. Traditionally, no. So once you ignite the propellants, basically it's going to go. But there are people that are working on different technologies to try to what we call throttling the propellant, to adjust how fast it burns at different times. But that's still a big challenge to do that. So as of right now, I'm not familiar with any fielded propellants that can do that.
So what types of majors are involved in your field, and can any student do this?
That's a really good question. This is one of the exciting areas, or exciting parts of this area, this field. My background is mechanical engineering. All my degrees are mechanical engineering, although I teach a lot of aerospace classes. And there's a lot of colleagues I have and friends in the field that are chemical engineers. There's some that are chemists, some that are physicists. And so there's actually a wide range of STEM disciplines that get involved in the propulsion area, depending on the perspective. And that's the key thing to think about, is everything involves science, right? So it doesn't matter what discipline you're in, you're just going to look at this problem from a different perspective. And so that's the exciting part, is that there's so many different possibilities of ways to get involved in this, depending on what your area of interest is.
So kind of a follow-on then from that is, what kind of key classes and experiences do you need to become an engineer?
So I think Shane mentioned it earlier when he mentioned the hands-on experience. So, obviously the math, the physics, the chemistry classes, those are all really good. But I can tell you from experience, it wasn't until in high school, I was part of a robotics team. that I really started getting involved in things. And that really teaches you so much. Not to say that the classes aren't important, right? You need to understand the underlying physics there, but really the hands-on part. So if you can get involved in classes and activities that really emphasize the hands-on perspective, the hands-on opportunities, those will be great, because then you're going to be able to go with those experiences and take what you know from class, the classroom and books, and apply them in real life. And that's what really will accelerate your career.
Okay, what kind of job openings are available in this field?
So there's a lot of interest, of course, in the military for these types of systems. Of course, different space exploration companies. A lot of them don't use solid propellants now, although I think NASA uses some. A lot of them hybrid or liquid rockets, but the underlying physics and chemistry are similar. So it's a lot of different aspects in terms of you can be involved with making a new molecule as a chemist, or you can be involved with testing this as a propulsion engineer. So there's a wide range of opportunities, depending what your interests are, really, which is the exciting part.
So what made you get into solid propellants?
So that's a good question. So when I was in grad school, I worked on aspects of particle combustion, and some of those particles are things like metals, like aluminum, that are used in propulsion. And actually, I worked for the Navy, China Lake, not too far away from Edwards, in the Antelope Valley, and that's really where I got most of my experience with solid propellants is there. Before that job, I probably couldn't tell you two things about solid propellants, but after that, that's where I really got my my start in this area.
So do your students actually make fuel and launch rockets?
So we can't make the propellant because of some of the limitations, the hazards with it. So we make inert variants of the propellant, and we study the individual ingredients. So by themselves, they're not as hazardous. And the students in my research group, we don't make rockets for research, but we have several rocket teams that I help mentor at Long Beach, and those students build rockets, launch them in the Mojave, and have done quite well in some national competitions